I don't know where and how this topic started dominating crypto Twitter in the last couple weeks. I think it was because of Solana, but maybe someone else can correct me maybe. But there's a lot of talk about parallelization in the last couple weeks. Can we very quickly, for the non-technical people in the spaces, what is parallelization and why is it important for blockchains?
Maybe before we begin, maybe I guess Jared and I could riff off of like what the background to this was.
Absolutely.
Yeah, so like, but I think this whole topic probably came to bear when inscriptions took off, and maybe Jared will probably describe what they are and how they function a bit better than I would. But essentially, inscriptions are where like there's groups of people who basically are running almost like NFTs, but in with some form of off-chain communication where they're using the call data to be able to like encode different bits of information. And the thing with them is that they led to like a ballooning of like transactions across various blockchains. And so we saw a lot of people, well, a lot of different blockchains really begin to buckle under the weight of like just what would have almost felt like a DDoS attack or something of that sort. And so we kind of began to see which chains would actually be stable and which ones weren't. And Polygon POS was able to really emerge as one of the stronger chains simply because of parallelization. And I promised actually to practice that word before I started, and I didn't do it enough, clearly. But yeah, parallelization. Jared, do you want to probably speak to this a bit more?
Yeah, I think that's a pretty good summary. I think there's two like trends that came up in CT that really brought about this discussion was first, like Tony said, was these inscriptions. You know, we saw like Polygon POS alone, I think it was nearly close to 200 million inscription related transactions in 3 or 4 weeks, which is pretty insane. And like you said, we saw some EVM chains were not able to handle this as well as Polygon POS was. I don't want to turn it into like a PvP discussion and call out different chains, but we saw some chains go down. We saw some chains have massive increases in gas fees, and it was just like a revelation of, well, you know, how much traffic can these different chains handle? And one of the main key factors in POS's success was this parallelization. And then the second thing I thought, and this just came to my mind now, was we saw, like you said, was a Solana discussion where this thing called Neon VM or Neon EVM. It's essentially like parallelized EVM on Solana. I don't have a good explanation of the specifics of how it works. I haven't done like a deep dive into it, but there was also like different chains like Say, I believe, jumping in on this parallelization trend, I guess you could say. And maybe that was like the snowball that was required to make this the hot narrative that it was last week.
Okay, great. Yeah, so given that, I'm gonna like speak to any of the POS engineers and ask them if they could give us a definition of parallelization. You could tell Jared practiced it a lot better than I did. Yeah, so Sandeep, Kojari, anybody else wants to speak up? And just give us like a general definition of what it looks like and why does it matter for blockchains?
Yep. Yeah, I can take on this one. So before diving deep into parallelization, we need to like understand, like I just go over, you know, how block execution works in general in blockchain. So in conventional blockchain like EVM, transactions in a block are executed in a sequence. So you say you have 10 transactions in a block, and then we execute one after one in a single CPU core. And now everything is executed in a single core, and that is pretty easy to implement. And there's now, in terms of parallelization, the challenge here is, can we expand this execution model to multi-core and therefore reduce the total execution time required to fully execute the block? So imagine that before you have one core executing 10 transactions one by one. Now you can potentially have, say, 10 cores executing one transactions all at the same time. And that can be potentially a 10x increase in terms of execution speed. Yeah, that's a very high-level brief introduction to parallelization.
All right, cool. So from my understanding of what you've said is that imagine you have a single lane road and you have cars that want to get through that single lane road. And the way blockchains currently work is that they could only process one car at a time, right? But if I have a parallelized blockchain, then I could essentially add more lanes and process more cars. Is that a good mental model for me to use as I begin?
Yes, that's a perfect analogy. Yes, imagine like previously you have only one lane, now you're trying to, increase the, expand these roads to say 10 lanes, and yeah, that can increase the throughput of the road.
Okay, great.
I just want to add another point here. Since you were bringing up the parallel with cars and lanes, there is one constraint though. Basically, in the blockchain as well, if there are multiple transactions, which are say affecting the same, or which are executing transactions, let's say for example on the same contract. Okay, there's a single contract deployed and say there are 10 transactions in the transaction pool. So these 10 transactions will have to still go through serially because they touch the same parts of the state as the other 9 transactions, right? So let's say, to draw parallels with the car example, if there are blue, green, red, and black cars, and if there are 10 black cars, those 10 black cars will have to still go serially in the same lane. And yeah, you can parallelize the red, blue, green ones, right? So hope that example makes it clear about the constraint itself.
Yeah, exactly. Yeah, I think that really does a really great job of like clarifying what that kind of look like. So I have a bunch of cars that are headed a particular direction. They should all follow each other. I have cars that could just go wherever they are, and like the destination is like a smart contract. And it makes sense for me to route all of the cars that are going a particular way, so that they kind of follow each other in sequence, and then allow the rest of traffic to flow however it actually works. Probably simpler way for me to do it, but like, yeah, I'm really dumb, so I need like the very like Eli 5 example to actually like conceptualize things usually. So yeah, that's super helpful. But then let's start to look at like where's the basis of this? There's like I'm sure there's a there's a basis for all of this. And in my understanding of this the whole concept of EVM parallelization came from the Aptos ecosystem. And I guess one of the things that I kind of saw that was really interesting there, and I was hoping that you could help define for us, is like the software transactional memory like algorithm that kind of decides all of these things. Could you like break down what that algorithm is, how it works, and yeah, basically how it kind of sorts? Is that how STM is essentially applied in a blockchain context?
Yeah, sure. I can take on this one. So block STM, which stands for software transactional memory, is a mechanism in software that would deal with concurrency. especially when there's potential possibility of say conflicts between transactions. By conflicts, I mean the car example here is multiple cars with the same color trying to get into the same lane. Now, so block SDM here, I can summarize it as a three-phase execution. So in the first phase, we're trying to optimistically execute transactions in parallel. So in the car example, you can think of okay. So before diving into these, the assumption here is that in the car example, we don't actually know the color of the car until we put the car onto the lane. So which means that we don't know where the contention or the conflicts are happening. So because in the blockchain world, a transaction can execute and they can touch on multiple different smart contracts, and without actually executing each transaction, we don't really know what the memory or the contracts these transactions are writing to. Therefore, in the car example, you can think like we don't actually know what color of this car before we drive it onto the lane. Okay, so the first phase of block STM is just optimistically execute the transactions and record the results of their execution. Right. So once we have the result of each execution of each transaction, then we enter this validation phase. We validate whether the result of each transaction is depending on basically we verify or validate whether a transaction is depending on the results of other transactions. Right. So if that dependency is detected, then we know, okay, could be potentially some problems here, and then we need to resolve that. So in the validation phase, we can send the transaction back to re-execution until everything is sorted out, that we know, okay, the transaction that should be executed before some transactions are all sorted out, and therefore we can trust the results of all the execution. And the third phase is to commit the changes that are made by these transactions to the final state, which is the final global state of the blockchain.
So very quickly, for those who are joining us today, we have a team of Polygon engineers who are joining us today to talk about parallelization on blockchains. And I think what Jerry has spoken to so far is one of the very few possible ways to process blockchains faster through what we are referring to as parallelization. And it all stems from the traditional way that blockchains have processed transactions, which is sequentially, which is you submitted your transaction first. So I will process this first, and then the next one, and then the next one. And that's a very cumbersome process. And the idea of parallelization is to process all of these transactions simultaneously rather than sequentially. And that comes into a new problem, which is that suppose somebody wanted to send me one Bitcoin and I wanted to send that Bitcoin to somebody else. You couldn't process both of that simultaneously because my transaction, the second transaction, would depend on the result of the first one. And correct me if I'm mistaken, but like what Jerry is speaking to right now, the idea of software transactional memory is the idea of like optimistic transaction, which is that you would process everything regardless of whether there is a conflict, and then the blockchain will automatically resolve these transactions one by one, sorting out the conflicts until they're all resolved.
Yep, that's very yeah, that's the right understanding.
Right. So just to kind of clarify from my perspective, and maybe this is like resonate with other people's understanding so far, is essentially you take everything because you can't, by default, you don't know if anything is related, right? So you take it all, execute it all at once, and then after that, you can kind of say, well, these X, Y, and Z transactions are dependent on one another, so we can't execute these in parallel. And then is the next step to just take those dependent transactions and re-execute them, or how do you actually resolve those like dependent transactions?
Yeah, so to give you a more concrete example, say that, for example, we have two transactions. Say Bob sent one Bitcoin, or say one Matic token to Alice, and the second transaction is Bob sending another Matic token to, say, Carol, right? So in this case, you can think of the second transaction depends on the result of the first transaction. And why is that? Assuming that initially Bob has two Matic, right? So he's sending one Matic to Alice. Therefore, we have to deduct the balance of Bob from 2 to 1 and add the balance of Alice, say, from 0 to 1. So now, after the first transaction, Bob and Alice end up with both one Matic, right? So in the second transaction, what we need to do is to deduct another Matic from Bob, from Bob, which results the balance of 0. So if you don't do this correctly, then you can potentially end up with, say, Bob having the balance of 1, because if we execute the second transaction prematurely, the Bob's balance has not get deducted from transaction 1, so therefore its starting balance is 2. And with these, basically we have to sort out this kind of dependency. And in a very high level, we can summarize that the dependency is defined by whenever a transaction, the execution of a transaction is depending on the output of the other. So you can think of the output of the other in this case is that the execution result of the second transaction is depending on the execution result of the first transaction. And all it matters is because the Bob's balance has been deducted in the first transaction. Hope that clarify your question.
Yeah, I think it does. So essentially, my understanding now is, okay, we've executed everything in the kind of first wave or the first stage. And then after that, we have a result where, okay, transaction 1, 5, and 12 are dependent on one another. Therefore, those can't be executed in parallel. We need to actually go back and say, okay, let's re-execute those in sequence, right?
Yes, correct. Yeah, so during the execution or in the optimistic execution, we record the read and write of each transaction. Therefore, in the validation phase, we're able to detect the dependencies between each other of these transactions.
So thus far, we've talked about what parallelization is, why it's important for a blockchain. I kind of want to sit into the practical experience with parallelization of Polygon. Thus far we were talking about software transactional memory, STM, and we talked about how this was inspired by Aptos's design. And there are a number of blockchains who are also experimenting with their own form of parallelization, say Monet, Solana. Can we talk a little bit about what Polygon's experience is? Like, when did we started implementing parallelization of transactions at the execution layer, and in what shape or form does it exist in today?
Yeah. So we started working on or experimenting parallelization of EVM in I think in early April or May 2022. And our first kind of prototype or first working version was kind of beta released in September while we're still doing a lot of testing. And now last year, 2023, in June, that's where we when we release public release the stable version of of Polygon the EVM parallelization. And I think one thing we need to clarify a little bit is that the parallelization or say block execution happens in say in two different scenarios. One scenario is the block miner collects transactions from transaction pool, execute them, put them in a block. That's block mining. And the second phase is when the rest of the nodes in the network sees this block and try to validate this block. That's what we call validation phase. So currently, the parallelization only happens when when the node is validating incoming block from a validator. So yeah, that's just something we want to clarify, and we're also planning to explain the parallelization in the future to block mining as well. Yeah, and then I guess we can go to more details in sooner after some time. But yeah, so right now we only do parallelization in block validation.
Okay, yeah, that's really dope to like I guess grasp, because like it makes it a little that a lot clearer. I mean, a lot clearer when the um when the transactions are actually being processed and like resolved. And yeah, the validation phase is where I guess the nodes actually pick it up and like, oh yeah, well, these are out of sequence, so um, um, transactions are then I guess resolved there. But like I was wondering if you could like help us like define a little bit, maybe go a little bit deeper into how aborts and retries are actually executed, because that's like a phase where you have the kind of resolution and how it actually functions. So could you like just help us shed some light on like
Sure.
what that looks like there?
Yeah, sure. Yeah, also before diving into this detail, I also want to emphasize that our current implementation of parallelization does not modify the consensus at all. So that's like one of the beauty that Block SDN brings to the table is that we don't need to modify the block formats. To be able to execute a block in parallel. Yeah, and later on we can also talk about a few things that we can even better optimize, but which will bring a little bit of changes to the block header and stuff. Yeah, but this is just something that I like to emphasize, that today we do not modify any specification of either consensus or block formats of EVM. Yeah. Yeah, going deep into how transactions are abort or retried. Like we mentioned before, in the optimistic execution phase, we have a mechanism of recording all the read and writes that a transaction during the transaction execution, right? So it's you can think of it as a table where the table records, for example, if the balance has been modified, if the smart contracts, the storage of a smart contract slot is being modified or read by the transaction. So after the execution, we validate these read and write of each transaction and compare whether the version that's a particular transaction read from the database is correct or from the memory is correct. And if we find a mismatch saying that the value that this transaction read has been modified, okay, maybe a better example, say Bob, in the previous example, we mentioned Bob sending Matic to Alice and Carl, right? In the first transaction, Bob sends one Matic to Alice, and in the second transaction, Bob sends another Matic to Carol. So in this example, we record that for the first transaction we need to read the balance of Bob. We also need to read the balance of Alice, and we write the balance of we modify the balance of both Bob and Alice. In the second transaction, we do the same for Bob and Carl. Now the detection of the conflicts happens when we see, okay, the version that I in the second transaction, Bob reads the balance. However, the balance or the version of that balance was somehow modified by transaction one after, right? So then we know that, okay, there's a conflict, and we have to re-execute the transaction. So that's when we retry. And during abort, so we abort the transaction whenever we figure out that, okay, something that I'm reading from is already being modified by another transaction, or something that I'm reading from is written by a transaction that should be already retried. So which means, like, if we need to retry transaction 2 and transaction 3 is depending on transaction 2, then we can abort transaction 3 immediately, and that will save some computation time and resource.
Okay, so just to clarify that last little part there. So once you've made the detection that transaction C has a dependency, you identify, hey, this can't be parallelized because of this dependency. And then what is kind of the next step? Does it just stop executing it, store it for later, or is it kind of, yeah.
Yeah, so if a transaction is, say, if we have detected a transaction with a conflict here or a dependency here, we look at the status of the transaction. If the transaction is in the executing phase, then we just abort it immediately. If it's already completed, then we will wait until all the previous dependency has completed, and then we send it for re-execution. So we will always put a transaction on hold until the its dependency are completed.
Right, that makes sense. So then a follow-up to that is, let's say a transaction has been kind of partially executed. It's in like the phase where it's being, computed, and here's the result. And midway through that, it gets canned because it has a dependency, or canceled because it has a dependency. Is there any wasted like resources there because you've spent time executing a transaction and then you cancel it? Is there like a wasted compute time, and who kind of pays for that if there is?
Yeah, really good question. Yeah, so there, in like you said, here it is wasted. There is wasted CPU cycles here, but just keep in mind that right now today, majority of the computers, even like our PCs had, have more than one core, which means that, usually we have like 4-core or 8-core CPU computer. So when we execute these transactions in sequence, only one core is being used, and all the rest of computing resources are basically sitting idle, doing nothing, right? So rather than keeping those CPU in an idle state, block STM bring them into the table, and then just start utilizing these CPU cores that was in idle states. So I wouldn't say it's really kind of wasted in a sense, because we are kind of using these CPU computation resources, and we're not, those cores are already there with the computer previously, and we're just kind of increase the CPU utilization of the entire machine, if that makes sense.
Yeah, I think so. So instead of, like, let's say if it's an 8-core CPU, instead of 7 of them just doing nothing, you kind of just make them work, and then if the work that's spent is wasted, if it's a canceled transaction, that wasted execution is better than it doing nothing, basically. Is that the correct mindset?
Exactly, yes.
Okay. Is there, I know this is kind of a broad question, but is there any like security concerns or risks in the way that you do EVM or parallel execution over the traditional, one by one?
So in the worst case scenario, imagine that you have a block where every single transaction depends on its previous transaction. For example, in this case, we can say all transactions are created by Bob, and Bob just sends, Matic to different accounts. So in this case, every single transaction needs to be executed after its previous transaction is completed. So in this case, we spend a little bit of extra time in terms of validating the result of each transaction. And yeah, in this worst case scenario, it will take a little bit of more overhead or a little bit of more time compared to as if we're executing the transaction, in serial, like without parallelization, basically. And another little bit of risk, but I wouldn't say it's risky, is there always could be software bug, and if it's not handled correctly, then we can potentially see like deadlocks, or resource not being released in the client node, and that can bring to, say, node not being able to proceed to the next block, etc. But since we have released block STM last year, we haven't seen any major issues of that.
Yeah, also add to that, like I think in the abort and retry phase, you can think of a few risks, like similar to what Jerry was saying, where there are conditions, due to which the resources are not released in time. But even to counter that, what we have also implemented is there's also a parallel thread of serial execution that keeps running, uh, as though there is no parallel execution, available at all. So in the worst case, it performs equivalent to, uh, uh, the execution engine without parallelization. So again, that's also one of the risk mitigation strategies that we have implemented.
All right, cool. Yeah. Yeah, that kind of makes sense from a fallback standpoint. So in case all else fails, like it could still perform sequentially. That's really cool. So let's probably move on now. and start to talk about like what the benefits of this whole system has been. Like, what has parallelization done? I promise by the end of this space, I'll have figured out how to actually pronounce it correctly. But what has parallelization done for the Polygon POS chain, and what are some of the things we've seen so far from your perspectives? And I'll actually ask each of you to
Yeah.
like give your own perspectives and views on this.
Okay, yeah, I can go first. Yeah. So yeah, since we have launched parallelization, we have seen a pretty good improvement in terms of the block propagation. So in board, the block is propagated only if the node has validated the block to be, to be a correct block, right? So which means it has to wait for the block to wait for all the transactions to be executed for that block before propagating that block to the rest of the node, and it basically its peers. So imagine that within the network, if all the nodes are somehow magically being able to process blocks much faster, say 2x faster than before, then it means that the time it takes for this block to propagate throughout the network is reduced, and that brings us a lot of benefits. The biggest one is that it reduced the number of reorgs that we have seen in the past. Before parallelization, I've usually seen some really big reorgs happening in the past, but since we have released parallelization, those reorgs has become smaller and less frequent.
Cool.
Yeah, maybe Sandeep and Pratik, feel free to add.
Year to less reorgs. Sandeep, your
Yeah.
perspective so far. Yeah.
Yeah, I think like Jerry was mentioning, the reduction in overall execution time, uh, especially for heavier blocks. It reduces reorgs, and it has a lot of other indirect advantages or benefits. That's also hard to measure. I would say overall the network health has increased significantly. There are lesser uh, incidents that are reported of nodes which are going into a wrong fork or encountering bad block errors due to some of these issues. And yeah, I think also apart from the reorgs, overall the execution time, when it decreases, it also allows for more idle time after all the transactions are executed. So that again has quite a few benefits which are I would say hard to measure, but I think again, like reinforce basically restating the fact that overall network health has increased a lot after rolling it out.
And we mentioned that parallelization on Polygon POS chain, this whole process and design, it came from mid 2022. So it's been a while since the chain has been running, processing transactions at the execution level simultaneously. And you also mentioned that it's not even fully complete yet, the parallelization. Could you maybe talk a bit about what's next, and what does that roadmap look like? I I feel like um, there will be, yeah, no, just generally, what does that roadmap look like, and what can we, as a non-technical user on the POS chain, like what can I expect?
Right, so I can take that up. So if we look at parallelization on Polygon POS chain as a whole, we have basically divided it in 3 different parts. The first part was to make sure that transactions are executed in parallel while the block is being executed. This is complete, and this is what is live on the mainnet currently. The second phase is where we enable transaction dependency. So remember, just like a few minutes back, Jerry and you talked about how the transactions are aborted and how they're how the execution is again repeated, right? If a particular transaction is aborted. Now this actually consumes some resources and as well as take extra time to re-execute this particular transaction. Now, what will happen is like if I take the same example as Jerry mentioned, let's say Bob sends 2 transactions. The first transaction is Bob transfers 1 matic to Alice, and then the second transaction is Bob transfers 1 matic to Carol. Now, what the miner will do in this case is that he knows that transaction 2 is dependent on transaction 1, right? So when creating the block with these 2 transactions in it, he will also put a separate note inside the block header saying that transaction 2 is dependent on transaction 1. So when other nodes in the network will re-execute transactions inside this particular block, they'll make sure that transaction 2 is not executed before transaction 1. So this will mean that there will be 0 aborts and 0 aborts of transactions, which will again lead to saving the additional resources that are used to re-execute this transaction, as well as save time for one more transaction execution. So this is the second phase of parallelization where we will enable this dependency metadata to be stored inside the block header. Now the implementation of this is already done and it is released in the stable release, but it is not enabled because enabling this particular enabling the addition of this one particular extra field in the block header will require a hard fork. So we have not done a hard fork yet, but we are planning to release or we are planning to basically enable this hard fork with the Cancun changes that are going to be enabled, I think, this quarter in the next couple of months. From this particular phase, user will again expect the execution time to further reduce, which will again result in faster propagation of blocks, which will in turn reduce the reorgs that we see, and overall the network will be even more stable. This was the second phase. Now, the third phase will be enabling block STM while mining a particular block. So currently we only have parallel execution when a block is being validated, right? But a miner execute all these transactions serially. So the team is currently working on executing the transactions in parallel when a miner creates a block. So here the ultimate goal is to basically fit as many transactions as possible in the block, that too within 2 seconds. And we believe that once we enable parallel execution in mining, we will be able to achieve this. And basically for that, we and also once this is done, we will also increase the gas limit to feel to fit in as many transactions as possible in the block. Now, this is the last phase of block STM or parallel processing on Polygon POS chain, where the parallel execution will be present both in mining as well as while validating a block. And again, from this, what users can expect is that more number of transactions will be included in the block. So again, the time to include a particular transaction will decrease, which will again benefit the whole network. And also if but like we might also think of putting some additional field along with or basically replace the metadata with something saying the miner will say that I have executed these transactions in this sequence. So it will again help the executor while validating the block to again schedule these transactions in the same order that the miner has processed, which will again significantly reduce the execution time there. So again, users can expect that their transactions will be included like in lesser time than it is currently, and also the health of the network will be good and the network will be stable.
Yeah. Also, just to add to Pratik's point, if you think about the network overall, if let's say there are 10,000 nodes in the network currently, it's only one node, the primary validator, who is actually producing the block, who would have to uh, execute the transactions and figure out the dependency and all of that. And once this validator adds the information, the transaction dependency information in the block header, the rest 9,999 nodes in the network will not really have to waste any CPU cycles, and they in figuring out the dependency, they just have to read the dependency the transaction dependency metadata from the header and execute the transactions in the same order as mentioned in the metadata. So that would also bring down the compute requirements by a pretty good extent, is what we also anticipate. But again, like Pratik was mentioning, this is yet to be implemented and tested. It's still work in progress currently.
Thank you, Pratik and Sandeep. I am a little bit conscious of the time. We're coming up to the top of the hour, and we have time for a few questions. If you have questions, feel free to request to be a speaker. I will let you on. And in the meantime, we have a written question that's been submitted. So maybe I'll read it out, and anyone can take it if they have something to say. So this question is coming from Soul, and the question is: besides enabling parallel execution, did the POS chain make any improvements to your DB to allow parallel reading or writing?
Yeah, I can take this one. So today, even today, we're with parallelization, we're already reading, from database in parallel, and yeah, although we're not writing everything to the database in parallel, because essentially that is not feasible in the database, in most of the database, I guess. But yeah, so the short answer is we're already doing that today as part of the parallelization block HTML. And that, like, in the future, we'll be also working on some interesting data structure improvements. Recently there's this this huge change from Geth that enables path-based storage scheme, and that is actually a huge improvement to the database performance. It reduces a lot of database read and write compared to its previous hash-based scheme. Yeah, so we're looking into all kinds of different methods to improve the database read and write performance.
Cool. Do we have anybody else from the audience who wants to ask a question? Going once.
I'm not seeing anyone so far.
Okay. Jared promised to sing for us if we have like 5 minutes at the end. So Jared, feel free to unmute and take it away. Everybody, the musical stylings of one Jared Watts. No? Okay. Well, the absence of any further questions, I have no choice but to hold this, um, bring this to an end. So yeah, thank you very much for joining, everybody. Massive. Oh, Jared, you want to say something?
No, I was just gonna make a joke.
Yeah, go ahead. Go ahead.
You can close it up.
Actually,
That's so good.
we have a question. Yeah, so go ahead.
Jared.
Yeah, hi. I have a second question. My question is that since Polygon POS has implemented parallel execution, then would you also implement local fee market to take advantage of this parallelism so that if you have any local hotspot, it will not affect the global fee market? This is what Solana is doing. So will POS do this as well?
Yeah, this is a great question. So yeah, we have been thinking about this for quite a long time. And essentially, what you're saying is, if multiple transactions are writing, or they're trying to write or changing the state of the same contract, then only them should compete for a higher gas fee, instead of other transactions that are not relevant. Yeah, so we have been thinking about these, and however, these is a little bit more, this is a little bit new to the EVM, world. And if we're bringing these changes, it's going to be, the EVM consensus might diverge from what Ethereum has today. So yeah, we'll think about these carefully, and then once we have some concrete ideas, we can probably create a PIP, Polygon improvement proposal for that, and then everyone can contribute, and contribute their ideas, and or maybe make suggestions on that.
Oh, cool. Don't mind. Just one more question. Will Polygon ZK EVM will each of the ZK EVM also implement parallel execution as well, so that in future you can have multiple ZK EVM chain, and each ZK EVM chain can also do parallel execution?
Yeah, I mean, zkVM can do parallelization, although I'm not an expert on this field. But I think, yeah, today, to be able to prove a block, we do have the capability of proving each transaction in parallel. So that is doable already today. And yeah, with that, I mean, it comes very naturally to think about executing, or even bring parallelization to the prover, zk EVM as well. So, but yeah, that is a little bit more technical on the side of the zk space. And then probably I'm not the best person to answer this question, and probably need to bring up my colleagues, who has more expertise on this field. Yeah.
Yeah, it will be great if I can hear any other opinion from other speakers.
Yeah, I don't think we are fully equipped to answer your question, but thanks so much for asking anyway. So
Yeah, thank you guys.
you're welcome. So I don't think we have any other questions. Unless anyone has any closing remarks or points, I will conclude this spaces in 2 minutes. Thanks everyone for joining today. We're happy to have you here.